Okay, hello everybody. Welcome to this lecture 3 of week 7 on the course on linear systems theory. Until now we had a good characterization of the reachable and controllable subspaces, which gave us a nice build up to the idea of controllability. What we possibly would have learned in our undergrad course on control, usually we were dealing with seesaw systems, and then we had that if the matrix C is invertible and the system is controllable and so on. So, now we have a bit of a generalization of that to MIMO systems, of systems which have more than one inputs, and we slowly build up to the controllability condition of the controllability matrix C being of rank n or having full rank. And we had some nice proofs also to the build up in terms of the reachable subspace, in terms of the controllable subspace and so on. And what we also saw is in the case of LTI continuous time systems, that the concept of reachability and controllability are just similar. So, if a system is reachable, it is also controllable and vice versa, and that the conditions are exactly the same to verify those in terms of the controllability matrix or even the dimension of the reachable or the controllable subspace. Okay, so, this lecture we will do a little more proofs on controllability. What are the other methods to prove? Sometimes these might actually be easy to verify because they might be computationally inexpensive and so on. So, we will see some of these proofs which are quite elegant to begin with, and we will also make towards the end of this lecture a nice connection between Lyapunov stability conditions and controllability conditions. Okay. So, the first okay, so let us begin with a brief recap of invariant subspaces. Some of it we had done in over here, right, in our module 3 lecture 2, right. So, where we had a brief introduction to linear to invariant subspaces. Okay. So, let us do a bit of a recap of that. So, given an n cross n matrix A, a linear subspace V of R n is said to be A invariant if for every vector in V, we have that A times V is also in V. And this comes with a couple of nice beautiful properties. First one is, if I have an n cross n matrix A, invariant subspace, okay, it should be a non-zero invariant subspace V of R n, a V, so this should be V in R n, then the following statements are true. So, if one constructs an n cross n matrix V whose columns form a basis for this curly V, then there exists a k cross A matrix such that A times V is V times A bar, exactly what we derived in this lecture of module 3 lecture 2. Okay. In addition, it also has another very useful property, that V. So, this curly space V, which is the subspace that is of interest, this subspace V has at least one eigenvector of A. Okay. So, we will begin by proving this. Okay. So, let us say, so what we want to prove is that this V contains at least one eigenvector of A. Okay. So, let us say let us begin with let B V bar be an eigenvector of A bar, and what do we know about A bar is that A times V is V A bar. Okay. Now, so this A bar is of dimension k cross k. Okay. Now, let lambda be this corresponding eigenvalue to this eigenvector v bar. Okay, what we know then is well, A times V with this small v bar is V A bar also with this v bar. Okay, now what do I know? That v bar is an eigenvector of A bar. So, in general what is how do I write eigenvectors? Lambda I minus A times V is 0, or in other words A times V is lambda V. Okay. So, this will then turn out to be lambda, because V bar is a vector eigenvector of A bar. So, the V capital will be as it is, and I have this one. Okay. So, now if I look at this expression closely, A V bar is lambda V bar. Okay. So, this has a vector form, right. So, these are all the same V's. Okay. Therefore, this vector V, which can be written as this one, is an eigenvector of A. Because I can write this as A times V is lambda times V. Okay. Now, the next thing, okay, now the next step to prove is does this V, okay, this small v belong to the subspace, the curly V. Okay. Now, how is V? So, V is of this form V times V bar, the small v bar, which means that this vector V can be written, look at this expression carefully, can be written as a linear combination of the columns of V, and therefore, this V times V bar, right, or which is equal to V, must naturally belong to V. And what we now proved is the statement that V contains at least one eigenvector of A. Okay. So, we will use that statement shortly in one of our proofs. Okay. So, the first theorem for today's lecture would be the following. So, we will be as usual interested in LTI systems, that too of continuous time. So, the LTI system 1 is controllable if and only if there is no eigenvector of A transpose in the kernel of B transpose. Okay. So, what does this mean? So, we have to prove both ways, right. So, first we assume that it is controllable and then prove that there is no eigenvector of A transpose in the kernel of B transpose, and then we will do the reverse, right. We will prove the converse then. Okay. So, let us start by with the first step. So, the proof. Okay. So, the first step of the proof will be, okay, assume the system is controllable. Okay. So, once the system is controllable, then we will check what is, then we will have to prove that every eigenvector of A transpose is not in the kernel of B transpose. Okay. Now, what do we do is well, as usual, right, much of the proof techniques rely on proof by contradiction. Okay. So, first what I will do is I will assume that there is an eigenvector of A transpose which is also in the kernel of B transpose, okay, which means that, okay, let me call this eigenvector to be x is lambda x, and please do not confuse this x with that x dot equal to A x plus B u. Okay. So, this is just the eigenvector, nothing to do with the state. Okay, with x not equal to 0. Now, if this eigenvector of A is in the kernel of B transpose, then this will satisfy this expression, B transpose x is equal to 0. Now, what we will show is that if this is true, that there is one eigenvector of A transpose which is in the kernel of B transpose, then the system will lose controllability. Okay. What is the controllability matrix? C was B, A B, so on until A minus A n minus 1 B. C transpose I can write as B transpose, then here I will have B transpose, A transpose, sorry, these are all transposes all the way till B transpose, A transpose to the power n minus 1. Okay. Now, I use this expression A transpose x is lambda x. So, first what I just multiply here by x, and the x will show up here. So, I will have here B transpose x, B transpose A transpose x all the way till B transpose A transpose to the power n minus 1 x, and this will be nothing but okay, B transpose x lambda B transpose x and so on until lambda B, power n minus 1 B transpose x. So, I just do nothing, I just start with the controllability matrix, take its transpose, multiply by x, and make use of the fact that lambda is the eigenvalue of A transpose with the corresponding eigenvector x. Okay. So, what do I know? Well, this B transpose is x, that is what I assume, right. I assume that let there be an eigenvector of A transpose which is in the kernel of B transpose, which means this will go to 0. If this is 0, then it actually means that C transpose x equal to 0 when x is not equal to 0. Okay. So, which means that the null space of C transpose is also the kernel of C transpose has at least one non-zero eigenvector, okay, and then which means that the dimension of kernel of C transpose is always greater than 1, okay, greater than or equal to 1. So, it is at least 1, which means that the rank of C, which is also equal to the rank of C transpose, is n minus the dimension of kernel of C transpose. Okay, where did we get this from? We get this from the rank nullity theorem, that rank of C transpose plus the dimension of the kernel of C transpose should be n. Okay. Now, if the dimension of kernel of C transpose is greater than 1, which would mean that the rank of C transpose would be definitely less than n minus 1, n minus 2 or whatever, but it will always be less than n because the dimension of the kernel of C is greater than or equal to 1, okay, which means that if rank of C is not equal to n, then this renders the system uncontrollable. This is a contradiction. So, I have a contradiction. What is a contradiction? That if there exists eigenvalue an eigenvector of A which is also in the kernel of B transpose. So, if there exists an eigenvector of A transpose which is also in the kernel of B transpose, then the system becomes uncontrollable, right. And therefore, if the system is controllable, then there is no eigenvector. So, this actually will not hold true. So, B transpose x will never be 0, right. So, that is what is the first part of the proof, right. So, what does the statement say? System is controllable if and only if there is no eigenvector in the kernel of B transpose. So, we started by again proving or assuming that the system is controllable, and then show that if this condition is satisfied, then the system becomes uncontrollable, which was the proof by contradiction. Okay. In the next part, we will do the converse. We will assume that the system is not controllable. Okay, if the system is not controllable, then the rank of C is rank of C transpose, this is less than n. So, what will I show here is that if the system is not controllable, I just want to see what happens with this eigenvector of A transpose, does it lie in the kernel of B transpose and so on. Okay. So, again I invoke the rank nullity theorem to rewrite this as dimension of C of the kernel of C transpose is n minus the rank of C transpose. Okay. Now, because the rank is always less than n, the kernel will always have a dimension greater than or equal to 1. Okay. Now, let us say there is an element x that belongs to the kernel of C transpose, which means that C transpose A transpose x can be written as, C is again the controllability matrix. So, this is B transpose A transpose, B transpose A transpose square all the way till B transpose A transpose to the power n times x. Okay. So, if x is in the kernel of C transpose, which means C transpose of x will be 0. What is C transpose of x look like? Well, C transpose of x looks like this one here, the first term here. Okay. And C transpose x is 0 means B transpose of x is 0, B transpose of A transpose x is equal to 0 all the way until n minus 1. Okay. So, we write that here. So, the first is 0, second term is 0 all the way till B transpose A transpose to the power n x. Okay, why does this term remain? That term remains because there is here the terms only go till n minus 1. Okay, what happens to this term now? Is this also equal to 0? Okay, the answer to that comes from the Cali-Hamilton theorem, which if I look at this, the last equation of this, that the statement says that each matrix satisfies its own characteristic equation, and therefore, A power n can be written as a linear combination of its lower powers, everything from here, right. So, the Cali-Hamilton theorem states that A power n, so here my A, so A power n can be written as a linear combination of lower powers of A, that would be from A power 0 till A n minus 1. That is obvious from this expression, right. So, I do not need to write down it all over again. Okay. Therefore, what is the problematic term here? This term times x, so can be written as B transpose A transpose to the power n x can be written as linear combination of B transpose x, then I have A transpose B transpose x and so on until A transpose n minus 1 B x, and all of these terms go to 0 because of this, because of the first term here, right, because x belongs to the kernel of C transpose, all of these terms go to 0. So, in the same way as all these terms here go to 0. Okay. And therefore, what do I have now is C transpose A transpose x is 0 or the 0 vector, okay, which means that if x belongs to kernel of C transpose, it also means that C transpose A transpose x equal to 0. Look at this carefully, and this also means that this A transpose x belongs to kernel of C transpose, and therefore, this kernel of C is kernel of C transpose is A transpose invariant. Okay. Look at what was the definition of invariant subspaces. That a linear, again I have a n cross n matrix A which is a linear subspace of V. This V is said to be A invariant if whenever I take a vector V belongs to V, this curly V, then A V also belongs to V. So, in my case here, this subspace V is the kernel of C transpose, right. What do? I take an element of the kernel x which belongs to C transpose, and what I see is that A transpose x also lies in that kernel of C transpose, and therefore, kernel of C transpose is A invariant. Okay. So, when kernel of C transpose is A invariant, then this kernel of C transpose by the second condition contains at least one eigenvector of A transpose. So, from the property 2, this kernel of C transpose must contain at least one eigenvector of A transpose. Okay. Now, since C transpose x equal to 0, we also have that B transpose x will be equal to 0, okay, from the first line of or the first entry of the matrix C transpose x equal to 0. Okay. So, what does this mean? So, where did we start with? We started by the assumption that the system is not controllable, and then we ended up proving that this vector x, okay, which was in the kernel of C transpose. Okay. So, this vector which was in the kernel of C transpose via this property of kernel of C transpose being A invariant, it contains one eigenvector of A transpose. Let me assume that this x is some x is its eigenvector. So, this eigenvector which is also in the kernel of C transpose now also satisfies B transpose x equal to 0. Okay. So, this means that if the system is not controllable, then there exists an eigenvector of A transpose which is also in the kernel of B transpose. Okay. So, that concludes the proof. Again, you may just want to write these steps carefully for yourself, and each of the properties that we are using are the one which we learned in week 2 and week 3. Okay. Another interesting test. So, this system again the same system is controllable if and only if this condition holds, A minus lambda I with B, the rank of this is equal to n for all lambda belonging to the set of complex numbers. Okay. So, it turns out to be pretty simple, this proof. Again we start. So, what do we have to show, right? So, the condition that we want to verify is this one, or what happens when this particular condition is satisfied. A minus lambda I with B is equal to n. This also means that rank of the same thing with the transpose will also be equal to n. Now, if I again look at the rank nullity theorem, I can write this as dimension of kernel of the transpose, right. So, it's an obvious reason why I take this transpose, A transpose minus lambda I B transpose plus the rank of the same thing, A transpose minus lambda I B transpose is equal to n. Okay. Now, this is pretty okay, right. If the rank of this is n, then it is easy. Then okay. So, then what am I left with? Dimension of kernel of A transpose minus lambda I B transpose, okay, which means that just remove this dimension, that the kernel of this guy can contain only the 0 vector, right. So, if there exists an x which satisfies this relation, then x should only be 0. Okay, this is also equivalent to saying the following. Okay, therefore, kernel of A transpose minus lambda I B transpose, this is the set of all x in R n such that A transpose x is lambda x, okay, and B transpose x equal to 0 again for all. So, this set is only the null set for all lambda in C. Okay. So, what does this mean? This means that there can be no eigenvector which is in the, so no eigenvector of A transpose which is in the kernel of B transpose, or no non-trivial eigenvector. Okay. Now, this is precisely the eigenvector test. And therefore, we conclude that if the rank of A minus lambda I times B equal to n, this actually means that there cannot be an eigenvector of A transpose which is in the kernel of B transpose, and therefore, the eigenvector test for controllability says that this system is actually controllable. Okay. So, that is a simple trick here. Okay. So, the next theorem will try to find a relation between the Lyapunov test or the Lyapunov stability proofs that we did, and is there a relation between controllability and stability. So, the first result in that direction is the following. So, we assume that A is stable, that all its eigenvalues are less than 0, then the LTI system is controllable if and only if there is a unique positive definite solution to the following Lyapunov equation, right. And moreover, this unique solution is equal to, of course, this is the Gramian integrated from 0 to infinity, right. So, we will do a proof of this. So, what is the assumption that, okay, we know that A is stable. Okay. Then if A is stable, we show that controllability is equivalent to finding a solution for this, or if I can find a positive definite solution W for this equation, this amounts to controllability. So, these are the two things that we need to show. Okay. First, we start with this equation, which is that A W plus W transpose A is minus B transpose implies controllability. Again, we use the eigenvector test. Okay, what does the eigenvector test do? The eigenvector test again has to do with the eigenvectors of A transpose, and then you relate that to the kernel of B transpose. Okay. Right. Okay. So, assume that this equation, okay, let me call it star for here, assume that this equation holds, right, and then we have to write down steps which will show us that this will actually lead us to controllability. Okay. So, now let x, which is not equal to 0, be an eigenvector of A transpose, which is associated with eigenvalue lambda, which means something like this: A transpose of x is lambda x. Okay. Then I just do this little pre and post multiplication. So, x star A w plus w star A x is equal to negative of x star B transpose of x. So, this x star is the complex conjugate. Because these lambdas can actually be complex numbers also. Okay. Now, if I write the left hand side carefully, that would look something like this, right. So, I have A transpose x star the whole transpose w x plus x star W A transpose. Okay, sorry, there is a little mistake here. So, this is W A transpose, this is also W A transpose. Okay. So, X star W A transpose X, this because of this relation will take the following form. So, I will have lambda star X star W x plus lambda X star W x. So, this will just be, so I am just like is almost like adding up a complex number and its conjugate, right. So, what will I what will I be left is just the twice the real part of lambda X star of W x. Okay. So, okay, again we will see where did we start with. We started with assuming that this is true, right, in such a way that W is positive definite, and then we were to show that it actually means controllability. Okay. Now, if this is true, okay, I just do X star pre and post multiply by X star, where X is an eigenvalue of A transpose associated with the eigenvalue lambda, then I end up with this expression. Okay. Now, what do I know about this? That because A is stable, this must be negative. Okay. Not only that, W is positive, so this should be positive. What do I have on the right hand side? On the right hand side I have, so this X star B, this can equivalently be written as something like this, P transpose of X whole square. So, this is minus B transpose of X whole square. On the left hand side, what do I have? This is strictly less than 0, this is greater than 0, this is strictly less than 0 because of the assumption that A is less than 0 or A is a stability matrix, okay. And therefore, B transpose X cannot be equal to 0, which means that this eigenvector of A transpose is not in the kernel of B transpose, which actually means controllability. Okay. I started again by assuming that this is true, right, and then showed that if this is true, that there is no eigenvector of A transpose which is in the kernel of B transpose, which actually means controllability. Okay. So, that concludes the first part of the proof. Okay. Now, in the second part, assume that the LTI system 1 is controllable. Okay. If this is controllable, then we will show that equation that this equation marked by star is actually true. Okay. So, so this is how the equation looks like. W A is minus B transpose, and by letting A bar equal to A transpose, Q is B transpose, I can rewrite this equation in the following way. Now, this is A bar transpose W plus W A bar is minus Q. This is very similar to saying A transpose P plus P A is minus Q, right, as in the Lyapunov stability proofs. So, now we will just use some of those techniques over there to prove that if the system is controllable, then there exists a positive definite solution to this equation. Okay. So, this expression tells us that if A is a stability matrix, A bar is also a stability matrix. Okay, so to conclude that W is the unique solution, we just make use of the proofs which we had in Lyapunov stability of the previous week's lectures. Okay, so what we need to show now is that this W is actually positive definite, and that this is also a solution to this equation. Okay, so the only problem that we will have here is that this minus B transpose, which we called as minus Q, is sign indefinite, or we can't actually conclude if this is positive definite or not. Okay, but what do we know? We know that the system 1 is controllable. Okay. Now, let us see if we can make use of this. So, let me just start with some arbitrary vector x transpose W x. Now, what is this W? Well, what I want to prove is that the W which is given by this expression is a unique solution. So, uniqueness I can prove, but now I will prove that this is actually the solution here, and is also that W is a positive definite solution. Okay. So, this will be x transpose. So, in the inside I have 0 to infinity e power A transpose B, sorry, A tau B transpose e power A transpose of tau with a d tau here and a x. Now, this is okay, can be checked that I can easily write this as this is greater than or equal to x transpose 0 to 1 e power A tau B transpose e power A transpose tau d tau, which is okay times x here. Okay. Now, this guy is just the controllability Gramian defined from initial time 0 and a final time 1. Okay. Now, because the system is controllable, what will I have is x transpose W r times x is always greater than 0, right, because of you can look at the definitions of the image of W r being so this all have to do with the rank of C being equal to n, and then we had relations between the rank of C with the image of the Gramian and so on. So, this is actually true because of controllability. Okay. So, this actually means that this W is positive definite. Okay. What did we use to show the positive definiteness? That positive definiteness follows from the controllability, and therefore, what again let us do a quick recap. System was we assume that the system was controllable, and we showed that this equation marked by star had a positive definite solution W. Okay. So, this expression looks similar to what I had in the Lyapunov stability theorem, just that there Q, for every Q greater than 0, I found out a P which was greater than 0, which satisfied the Lyapunov equation. Okay. So, the uniqueness and all I can establish from there. What I just show here is that this W indeed is positive definite, which follows directly from the assumption that one is controllable, and which concludes the proof here. Okay. So, the last result of today, we'll quickly wind up with the proof, shows that, so we had earlier 5 conditions of stability. It started first with the eigenvalues being strictly less than 0. This was equal to asymptotic stability. This is also equal to exponential stability. Then we had 2 equivalent conditions to prove that for any positive matrix Q, there existed a solution to this expression. So, given a Q, A transpose P plus P A equal to Q, this also meant asymptotic stability or exponential stability. Similarly, with this A transpose P plus P A less than 0, all these were equivalent, starting from eigenvalues being less than 0 to asymptotic stability, exponential stability, and these two things. So, what we have okay, that in addition that we have this one. So, for every matrix B for which the system or the pair AB is controllable, which also means that okay, the system written by x dot equal to AX plus BU is controllable, then there exists a unique solution P to the Lyapunov equation given by this. Moreover, this P is symmetric, positive definite and equivalent to this expression. Okay, so the proof will just make use of all the little tricks that we used in today's lectures of the earlier proofs. Okay, so we need to show that this condition A transpose P plus P A is minus B transpose actually means asymptotic stability or even exponential stability. So, in the previous expression what we had in the previous theorem, this condition, okay, we started with when A is stable, then such a situation then such a equation is satisfied with W being positive definite and taking this expression. Okay. So, now we have to show a bit of the something like the converse of it, that if A transpose P plus P A is minus B transpose, then this will also mean that the eigenvalues of A are strictly less than 0 or the real parts. Okay. Let us assume now that this expression holds, and as usual let x be an eigenvector associated to the eigenvalue lambda. Okay, the same tricks again, x star A transpose P plus P A times x is minus x star B transpose x is minus B transpose x whole square. Okay, again this is the complex conjugate. Okay, now very similar tricks as we did earlier. So, this the left hand side can be written as A transpose x star transpose P x plus x star P A transpose x is again making use of this expression here. I have this to be lambda star x star P x plus lambda x star P x. Again this will give me twice real part of lambda x star P x, and on the right hand side I have minus B transpose of x whole square. Okay. Now, what do I assume? So, this condition I know is equivalent to controllability from this theorem, right, from this theorem here. So, this theorem just tells me about controllability, right. So, if system is controllable if and only if I can solve for this expression where W is a positive matrix given by this expression here, or W is actually a positive definite solution. Okay. Now, because of controllability, okay, because of controllability, what does controllability tell me? If the system is controllable, which means that there is no eigenvector of A transpose which is in the kernel of B transpose, means this should definitely not be equal to 0. Okay. Now, P, look at these expressions here. Now, this is not allowed to be 0 because the system is controllable. So, this should definitely be less than 0. X conjugate Px is always greater than 0 because P is greater than 0. Now, I am just left with this term, and what should the overall term be? Overall term should be less than 0 because this is not allowed to be 0, and then I have the norm with the square. So, this number should always be less than 0 because of the negative sign here, and therefore, the only solution left is for the real part of the lambdas to be greater than 0. This shows that A transpose is a stable matrix or a stability matrix, and therefore, A is also a stable matrix. Okay. So, starting from this, assuming that this expression is true, we followed these steps, made use of the fact that this because the system is controllable, there is no eigenvector of A transpose which is allowed to be in the kernel of B transpose, which led us to conclude that A transpose is a stability matrix, and therefore, A is also a stability matrix, right, and this means exponential stability and also asymptotic stability, right. So, this concludes the proof of this result. A bunch of things we derived today, starting from the definition of controllability and then to do with some eigenvalue eigenvector properties of A transpose and B transpose. We also found out a beautiful relation between controllability and Lyapunov stability. Okay. So, these are details which you may, it may help for you to work it out by yourself and check for those proofs again. So, in the next lecture we will talk about controllability for discrete time systems. So, are the properties, can we just directly take this and put it there and everything will fall in place? Okay, that we will see if the discrete time systems throw up some surprises or everything is just copy paste appropriately. Okay, so that's coming up in the next lecture. Thanks for listening.